Okay, so let's go ahead and use our Arclength formula for some real-life problems. Again, remember our arc length is the radius times theta, and again we are measured in radians here. So that's this is a good formula if we're in radian mode. So the first problem says we got to find the radius of a pulley if a rotation of 70 degrees raises a weight 12 centimeters. Okay, and that's like, whoa, what's going on there? Picture-wise, here's what's happening, right? I've got some pulley up here that is basically an unknown radius, and as any pulley will do, right, we have some rope or the chain, and what we use pulleys for is to basically move weights up and down, all right? And so what we know is that somebody's been pulling on this rope or this chain, and it's basically moved this up 12 centimeters. And we know that this right here rotated 70 degrees. So there's a picture of what's happening. I guess, you know, that 70 degrees would technically be right in there. So there was a 70-degree rotation, right? And that 70-degree rotation caused the weight to move up 12 centimeters. So essentially, what we're going to have to do first off is assume that there's no slippage. Right? We're going to assume that the friction between the rope and the pulley is exact, all right? Or maybe we have a chain and we have a gearbox and it's intact, so where there's no slippage here. So basically, if this has moved up 12 centimeters, right, that means that we have moved, let me change colors, on the pulley, we've moved 12 centimeters along that pulley in terms of arc length. So essentially, there's my arc length. And the theta right now, unfortunately, is 70 degrees, but this formula we have only works for radians. So the first thing we need to do is take that 70 degrees, right, and convert it to radian mode, right? Zeros cancel out, so we have 7 pi over 180. So I have some nice, neat fractions, so let's do the fraction work. So my arc length is r times theta. We know the arc length is 12, the radius is not known, and we just figured out that the central angle is 7 pi over 18. I'm sorry, I canceled out those zeros, huh? Alright, so 7 pi over 18. So to solve this, right, probably the coolest thing to do is to multiply both sides by a reciprocal. Okay, and that gets r by itself. And doing the math, I don't see any cancelizations over here. So 18 times 12, right, that's a pretty big number, 16, 1, 36, 18, 6, 1. So we get 216 pi, oops, 216 upstairs and 7 pi downstairs. So there's our nice exact answer. This would be in centimeters since our arc length is better than centimeters. So again, I'm trying to live up to what I'm expecting out of you guys, and we need some work on fractions. So I'm gonna force the issue. So I have a nice, neat integer, right? Nice, neat fraction for my central angle. Let's work on the fraction work and learn how to solve equations with fractions. Let's improve that skill. Okay, and there's your pulley problem. Right? I think there's a couple of those in your homework, etc. So the next one is a little different. We actually have, you can imagine there are two gears, right? So we have a rotation of a larger wheel, right, causes the smaller wheel to rotate. So I hope we can appreciate that. You know, as this guy rotates, this guy is also, right, as this guy moves around, this guy is also going to go through some rotation as well. So one thing is going to cause the other to rotate. Classic case 2 is on a bike when we have a sprocket and a chain. Okay? So how's this going to help us out? Well, it says that if the large wheel rotates at pi over 3, what will the amount of rotation of the smaller wheel be? And so again, what we're going to do, like we just did in the last problem, is we're going to assume that there's no slippage, that either the gears or the chains or whatever that are connecting these things are true, and the chain's not slipping. Because that does mean then that as this guy rotates as we go pi over 3 rotation, and I create some sort of arc length here, right, because of no slippage, this arc length is also going to be the same right here. So the arc length and the arc length are going to match, right, for each wheel, because as we rotated, we went through that distance, if you would, on both wheels. So essentially, let me write it this way. We have the arc length of the smaller wheel should be equal to the arc length of the bigger wheel. All right, so I'll call the smaller wheel S sub S, and I'll call the big wheel S sub B. What do we know? Well, according to our formula, right, for this guy, it's the smaller radius and the angle, right, of a central angle for that. And here it's the radius of the bigger guy and the central angle for the bigger guy. So again, just using some indices to distinguish the radius of the small versus the radius of the big, the central angle of the small, the central angle of the big. Now, right, now that we've got that all set up, we just substitute what I know. This is 4, right, so 4 theta s. The big radius is 10, and we were told that that central angle is pi over 3. So again, everything is in integers and nice fractions, so we are going to find the exact value. So we got 10 pi over 3. Again, perhaps I multiply both sides by 1/4, right? That'll clear the 4's on this side, and we end up getting 10 pi over 12. Of course, we can do a reduction, right? This turns into 5 pi over 6. So as this wheel rotates around basically 60 degrees, right, that's pi over 3. This wheel is going to be rotating 150 degrees, right? That would be the degree thing for there. So that, to create this same amount of thing here, right, because this is a smaller wheel, right, I'm going to have to do more rotation to match the arc length that we had on that bigger one. Okay? So there you have it. So the classic arc length equals arc length formula. So we actually have some inside information for the next one. So again, very similarly, we have a rotation of a small wheel causes the large wheel to rotate. So it's now the smaller wheel that's rotating, right? The smaller wheel rotates 120 degrees. What will the amount of rotation of the large wheel be? And again, what we have is the arc length of the smaller should equal the arc length of the bigger, right? So the radius of the smaller times the central angle of the smaller should equal the radius of the bigger and the central angle of the bigger. All right. And we just need to plug things in. We already know the radius, right? Again, we have a couple of decimals, so I'm struggling here. Should we use fractions? Let's use fractions, okay? Again, we need to get better at this skill, all right? So I'm going to use fractions here. Of course, since there's a couple of decimals, you can turn to your technology. This smaller wheel, well, that's 325 over 100, right? And then theta s, we'll figure it out in a moment. This radius is 105 over 10, and we have theta b. Okay, so I've converted everything into their fractional form, and we can basically reduce that, which I'll do in a moment. What about theta s? Well, unfortunately, it's measured in 120 degrees. So the formula I'm using here only works in radians. So what I'm first going to have to do is take my 120 and convert it to radian degree, right? And so that, I think, will be 2 pi over 3, right? 60 goes in there twice and goes in there 3. So we have 325 over 100 times 2 pi over 3, right, equals 105 over 10 and theta b. Okay, and you can kind of see what's going to happen. I'm going to reduce this at the end. To get this guy by itself, I'll multiply both sides by 10 over 105. And what we now have is just a huge exercise in basically simplifying this fraction. Of course, we could have done it earlier here and here, so everything's a little easier to work with, but I went ahead and just did that. So how about, I know 25 goes into here 4 times, and I believe 4, 4, 4, and 13 times. And then I don't see anything else dividing out with anybody else. So it looks like we have 20 and 13. That would be 260, 520 pi, and then we have 105 times 12, so we get 2 and 105, 06, 210, and we get 1260 on the bottom. So I guess we do have something that, oh yeah, I see it. I should have canceled it out here, but we can see, right, there's some 0 cancels out, right, and then 2 goes into there 26 times, and I think 2 goes into there 53 times. So after all our simplification, right, the central angle of the big guy is 26 pi over 53. Okay, so again, just trying to simulate what I want you guys to be able to do on a test, because I'm not trying to be mean. I'm not trying to be a mean guy. I know calculators are wonderful, but just watching you guys work over the last 4 weeks, we're struggling with fractions. So I'm going to try to force the issue and make you work with them. And so that's why throughout this sheet, all my answers, all right, are nice. Maybe they're not nice, but they are exact fractional answers. All right, and expect the same thing out of you guys on a quiz. So make sure you're listening. That wraps up arc length. We're going to go look at area in the next video.